Hello guys, today I'll be explaining the physics AMS of term 1 week 3. But before I start, I would like to say that don't rely on this physics quiz, it's not that beneficial because there are so many other concepts I might explain when we finish the quiz, okay? So first of all, the nuclear reaction where a heavy nuclei splits into two lighter nuclei upon bombardment by a neutron is called fission. Now we have two types of nuclear reactions. We have fission and fusion. Fission, you have a heavy nuclei, and so then you shoot a neutron at the nuclei and it becomes two lighter nuclei. I'm gonna name them A and B, okay, with many other neutrons. Now, fusion is the opposite. You have two light nuclei, let's say A and B, they come together and they form what? One heavy nuclei. Fission has less energy than fusion, but it still has a great amount. So big amount, fusion is a bigger amount. So this is for this question. Question number 2. Okay, which of the following are disadvantages of nuclear energy? So nuclear energy, which is either by fission or fusion, okay, we have certain advantages and disadvantages. I'm gonna explain it even further because these did not come in the quiz, but I would like to explain them because they might come in the exam. Now, advantages of nuclear energy, they include what? Less pollution, greenhouse effect, and also the global warming. Another advantage is that the moderators produce their own fuel. That means less fuel is needed because they produce their own fuel. So these are two advantages for the nuclear energy. Now let's talk about disadvantages. Okay, we have, for example, it's very costly, it's very expensive. So in poorer countries, they cannot afford to have a nuclear power plant. Okay, the waste is very radioactive and very dangerous if not stored properly. So it should be stored in a lead with a lead room. Okay, and another thing is the psychological bias, meaning that people are afraid of it constantly. For example, in Chernobyl, there was an explosion that happened because of a nuclear factory. And so people are constantly, they are fearing that something is gonna happen. So it will affect in the psychological bias. Now they're talking, what are the disadvantages of nuclear energy? Now, in case of failure of the protective covering, so if they didn't use lead, for example, radiation can seep through the environment and it can cause many diseases such as cancer, generational diseases and stuff like this. Now, nuclear plants pollute the environment with greenhouse gases? No, in fact, they reduce they reduce the effect of emitting greenhouse gases. Okay. Now, if they are not stored, okay, the half-life of the nuclear waste is very long, so it will contaminate very much. Okay. Nuclear plants significantly contribute to global warming? No, they do not. At all, they don't. And then finally, a very large amount of fuel is required to run a nuclear plant? No, they don't need a lot of fuel. As we said, they can make their own fuel. For example, uranium can make its own fuel, so you don't need coal. And one fact I think you need to know is that 1 kg of uranium gives the same energy as 10,000 tons of coal. So a kg of uranium gives the same energy as 10,000 tons of coal. So it produces its own fuel, so it doesn't need a very large amount of fuel. Question number 3. Which of the following are advantages of nuclear energy? So before we spoke of disadvantages, now we're talking about advantages. Psychological bias, we said, is a disadvantage. Okay. We said it does run on a smaller amount of fuel. Yes. We said it can't be built everywhere. It's very costly, so poorer countries cannot build it. It does not contribute to the greenhouse effect. Very good. That's very true, sorry. And power plant does not require protective material. No, it does. It does require to, like, the waste required to be put in a lead container so that nothing like will radiate out of it. Question number 4. Now we reached energy. For example, we have energy. Energy, what is the definition? Energy, what can it do? It is the ability to cause a change. So, energy is the ability to cause a change. So it can be transferred from particle to particle, as an example. Or for example, to write on my screen right now, I'm using energy. Okay? There are many different types of energy. Now we're gonna talk about internal energy. Internal energy, they're divided into 3 parts. We have the random kinetic energy. Then we have the chemical potential energy. And then we have the intermolecular potential energy. Now, random kinetic energy is the random movement of particles. So when we're talking about internal energy, we're mainly talking about atoms. Yeah? Atoms or particles. Okay? Random kinetic energy, it is the movement of these particles. Chemical potential energy, these particles, these atoms, they are bonded. So the bonds have what? Chemical potential energy. And the intermolecular potential energy is the energy stored in these particles. So that means the internal energy of a system can be thought of as the sum of the random kinetic energy, the intermolecular potential energy, and the chemical potential energy of its particles. Number 5. Depending on the context, okay, this is very important. So first we talked about internal energy, now we're going to talk about heat energy. Now heat energy, there are 3 types of heat energy. We have the radiant energy, or light energy. I'm gonna put here under it light. Then we have the thermal energy, which is basically heat. And then we have the internal energy. So the 3 types of energy from heat energy are radiant energy, thermal energy, and internal energy. We know what are the 3 types of energy in internal energy. They are random kinetic energy, chemical potential energy, and intermolecular potential energy. So here we are talking about heat energy. I forgot to mention that the thermal energy is random, so it can refer to a random thermal energy, a internal external energy, an internal energy, or a radiant energy. Radiant means light energy. Question 6. Which of the following are the uses of radioactivity? Now we have many uses for radioactivity. We have tracing. For example, you take a pill in the hospital, and with using radioactivity, they can trace how they can trace, for example, how your digestive system works. Then we have thickness measurement. So, for example, if you need something to be exactly, for example, you need a bunch of papers to be exactly 100 centimeters long. It's very long, I know, but let's say exactly you need it this thick, for example. You're gonna use radiation, so it will be exactly 100 centimeters thick. Then we have the carbon dating or radioactive dating, so we can find out the age of what? The age of really old bones and basically our historical stuff. And medicine, we also have radioactivity used for medicine. It's very important. For example, they use radioactivity to kill the cancer. Even though radioactivity can cause cancer, they also use it to kill the cancer cells. Another one is luminous scales. Basically something that emits light. And then finally we have food irradiation. So it will remove it will sanitize or sterilize food. And insect control. So radioactivity is beneficial for tracing, thickness measurement, carbon dating, medicine, luminous scales, food irradiation, and insect control. Now, based on what we just said, which of the following are uses of radioactivity? They don't measure the distance, but they measure the thickness. You cannot determine the brightness of a star using radioactivity, because how are you going to do it? You're going to shoot the radioactive particles to the stars? It doesn't make sense. Yes, it is for tracing the paths of reactants in biochemical reactions. This is very important. It's determining the age of samples by their radioactive activity. Also very important. And for sterilizing food products. So this is food irradiation, this is tracing, and this is carbon dating. Question number 7. A current flows in an electric circuit. A battery provides energy to the circuit. So the energy goes from the chemical energy in the battery. So this is chemical. And it provides energy to the circuit. And what does the circuit do? Probably it will do, for example, if it's a light bulb at the end of the circuit, it will make light. Or if it's a fan, it will turn, it will do mechanical energy, kinetic energy. So the energy is transferred from the battery, which is kinetic, and then it becomes electric energy in the circuit. And if it is a light bulb, it will be transformed into light energy plus heat. Question number 8. This is very important. So we have electromagnetic radiation. Let's take these examples here and let's explain them. We have infrared radiation. It can be used for night vision. Then we have X-rays. It is used in hospitals. We have microwaves. They heat food. We have gamma rays. Gamma rays can be used for medicine. And finally, we have radio waves. They are signals. So that means night vision, we said, is infrared radiation. A food heater is a microwave. We have another one here we didn't speak about before. Ultraviolet. The ultraviolet, now what I know about the ultraviolet is that it's really dangerous for our skin, but it's also beneficial somehow. I've forgotten which way. Now we said medical imaging in hospitals is X-ray, and whenever you have a signals or a broadcasting tower, it is what? Radio waves. Question number 9. Which of the following objects contain chemical potential energy? Chemical potential energy can be stored in batteries. It can be stored in food and in fuels. So atoms in a random motion, if they are moving, then they have kinetic energy. Anything moving has kinetic energy. Atomic nuclei has nuclear energy. And also the internal energy, which is the intermolecular energy. A fossil fuel, we said, is chemical, and food is also chemical. So the only two that have chemical potential energy, not moving, the potential energy, is fossil fuel and food. So detecting the leakage in the walls of a pipeline. So if we are detecting where the leakage is, okay, for example, we have, here's the house, okay, we have the pipe over here, and we have another house over here, and so on. But we have a leakage over here, and they don't know this is the surface. They can't open the ground to find out where is the leakage. So what do? They take a radioactive source, they put it here, it will go in the water flow, and if it stops over here, we know there is a leakage. So then they used which method? They used tracing. There's no such thing as scaling, probably the luminous scales, which is light, and dating is checking how old something is. Now, measuring the quantity of carbon-14, this is carbon dating, left in a bone, it's good for determining its age, as we said previously. Question number 12. An important factor that must be taken into consideration when safely burying the nuclear waste. The waste is very radioactive, so you need to bury it in lead. So, lead, like, you have to first of all find out what is the half-life of this waste material, because if it's very radioactive and the half-life is very, very, very long, it's gonna be really dangerous. So you have to keep it in a very strong lead box, for example. But if it is, for example, alpha radiation and the half-life is very, very tiny, not too long, you can put it in something not as much as lead, because lead is very expensive as well. Question number 13. Underline the term that describes the ability to cause a change. The ability to cause a change is energy. Question number 14. This is very important. There is a table we have to memorize. We have the dose and we have the particle and we have the dose. We have alpha, sorry for the bad handwriting, alpha is 1. We have, alpha is 20. We have beta is 1. And then we also have gamma plus X-ray is 1. But then we also have neutron. It is between 1 and 20, depending on the speed of the neutron. So this is very important to remember. I'll just write the symbols. Alpha is 20. Beta is 1. Gamma plus X-ray is 1. And then neutron, I will call it N. It is between 1 and 20. So here they need 2 rads of alpha particle radiation. So you do 2, the dosage, multiplied by what we know. So the alpha particle is 20. So 2 times 20, it's going to give us 40. Now 30 rads of beta radiation. So 30 times 1, it is going to be 30. 50 rads of gamma radiation. So 50 times 1, it is going to be 50. And 0.5 rads of X-ray, so 0.5 times 1, it is 0.5. So definitely they want it from the highest dose is 1. That means 1 is 50, 2 is 40, 3 is 30, and 4 is 50. Again, I will repeat how we did it. We have to memorize that alpha is 20, beta, gamma, X-ray is 1, and then the neutron is between 1 and 20. So we took the number and we multiplied it by the dose. Here we had 40, here we had 30, here we had 50, and here we had 0.5, and accordingly the one with the higher was the most dangerous one. So let me answer it. I forgot to answer it. So this was 2, this was 1, this was 3, and this was 4. Now the final question, I will probably do a summary after I submit. The diagram below shows an automatic setup used to check whether the level of yogurt in a cup is above a certain level. Now, what are they doing here? They are probably doing decontamination or food irradiation. So they're gonna use something that isn't very ionizing, and it's not too fast, and it has a long half-life. Okay, so if they are doing something with food, anything with food, it needs to be not too much ionizing, okay, and it shouldn't be too fast, meaning it doesn't have it has to have a long half-life. So we know alpha is very ionizing, okay, but it has a really short half-life. A really long half-life. No, never mind. Forget what I said there. Just know that beta is less ionizing than alpha, and it has a long half-life. Okay? This is important to know. So anytime they ask you anything with food, it's beta radiation. It has to have a long half-life. Why? So it lasts longer. Okay? Because you're unradiating this food. So let's submit, and then I will explain some other extra material. Okay? So, sorry if I posted it late because I was trying to get as much notes as possible. So we have radioactive benefits. What are they? We have tracing. We have thickness measurement. We have dating, not date like carbon dating. We have medicine. We have light sources or luminous scales. And finally, we have food irradiation and insect control. So, I think I've explained all of these. This is just something to remember. Another thing, if for example they gave you to do carbon dating, they told you 320, so then it became what in the end? It became, let's say not 40, it became 80. They want to know how old is this if, let's say, the half-life of carbon is approximately 6,000. Okay, just an approximation. What do? We have to take each half-life by itself. So 320, the first half-life, it becomes what? 160. Then 160, the second half-life, if you do half of 160, you will get 80. So how many half-lives did we get? We used 2 half-lives. So we know that the half-life of carbon is 6,000. So that means this here is 6,000 years, and this here is 6,000 years. So all in all, it will be 12,000 years. Please don't forget this. Another thing is the what high radioactivity causes. So high radioactivity, it causes immediate death, so death. It causes cancer. It causes genetic aberrations. aberrations, which means that like if you don't get affected by the radiation, your other generations will. And then we have loss of hair and sores. The maximum amount of radiation a person can receive in their lifetime is 10 rad. Okay, then we have the table. I'm just gonna make it a quicker summary. So alpha was 20, beta, gamma, x-ray were 1, and the neutron was between 1 and 20. By controlling the concentration of the radioactive materials, which is the quantity and the speed of the neutrons, that is the concentration, the rate of fission or fusion is controlled. Now, we talked about nuclear energy. Okay, let's talk about the energy, some energy. We have one main source of energy, not one, but like a big source of energy, which is heat energy. So heat energy, it is divided into 3 parts. 1, 2, 3. The first part is random thermal energy. The second part is radiant or light energy. The third part is internal energy. And as we know that internal is divided further into 3 parts, we have the random kinetic energy. Then we have the chemical, I'm just gonna write abbreviations, the chemical potential energy, and we have the intermolecular potential energy. Then, this is very important. We have Einstein's equation, which is E equals mc squared. So E is energy. Energy equals mass times the speed of light squared. Speed of light is 3 times 10 to the power of 8. So in this case, it will be 3 times 10 to the power of 8 squared. And, one more thing. So now more on radiant energy. Okay, just some quick topics. Radiant energy can travel through matter, and in vacuum, the speed of light is 3 times 10 to the power of 8. Now, there was a conflict between Einstein and some old generation scientists. Einstein said that light was particle or a body, and the old generation scientists said they were waves. So how do we prove they are particles? We do something called the photoelectric circuit. And how do we prove it is waves? By something called interference. Now, radiant energy has no mass, but it has momentum. And because of this conflict, they came up with one idea. They called it a photon. This photon is what? It is waves plus particle. Okay? Now, the color of light depends on how much energy the photon has. And this is very, very important. Energy is proportional to the frequency. Energy, this is alpha, or proportional to the frequency. And energy is inversely proportional, so that means you put 1 over the wave length. Or in other terms, if you have a high energy, you will have then a high frequency and a low wavelength. So this is all what I'm able to give for the exam tomorrow. Please revise on your own, and I hope you understood, and thank you for watching.